Newton Fellowship, and he moved to University of Southampton, UK, for his next postdoc. And since 2021, he is working at IIT Hyderabad. His research interests are high energy astrophysics, in particular active galactic nuclei and X-ray binaries and reverberation mapping of AGNs and these compact objects. So in addition, he is also a member for India-based like AstroSat mission and also international missions such as Chandra and ESO-based missions and radio missions such as e-MERLIN. So today he will talk about characterizing bright non-nuclear X-ray sources from Chandra ACIS sample. So yeah, you can.
Thank you. Thank you very much for the introduction, and thanks Professor Kuntal for inviting me and hosting me here for a week. So this is my first visit to ARIES and I'm really thrilled by cold and also the surroundings. So many, today's morning, Bhavya took me to the telescope facilities here. And I think day after tomorrow, we will be visiting to the Devsthal. So it will be a nice week for me, and I have two students here who are also present. So in today's talk, I'll be talking about a sample survey with Chandra. So basically now ARIES is like a place for optical astronomy. So all are like centered around optical bands. But here I'm going to present something outside optical. Okay, right. Yes. Okay. Okay. Right. Okay. Okay, right. Okay. Good. So, so in this work, which I have started during my postdoc at Southampton, and then I carry forward while I shifted to IIT Hyderabad, and now one of my students is working on the same topic. So basically, what we did, this started with David and Ranieri and then Ian. They are actually the PI of e-MERLIN radio telescope. It's a group of 6 radio telescopes in UK. It's an array of 6 telescopes, and it has very decent radio resolutions. So we decided that what we'll do with this telescope, and then we'll write proposals for Chandra. So jointly we performed the survey of nearly 200 nearby galaxies using radio and Chandra together. The purpose was to find out the best radio image and the X-ray together and find out the radio X-ray correlation related studies. So all these fields contains the AGN plus lots of other X-ray sources. And then David led the work on the AGN. So he worked on the radio and X-ray properties of the AGN. Later, I took the lead on the other projects, which is all the off-nuclear sources, means all the X-ray sources which are in the field of ASIC, Chandra ASIC, but not the AGN. So the aim of these projects for my part is that we have the data for all 211 nearby AGN galaxy fields. These 211 AGN galaxies are chosen by the Palomar sample. And then for each of this field, you pick up the best X-ray sources, best in the sense the high signal to noise ratio, and you have lots of counts. Then you try to find out the temporal variability and the spectral variability. So I'm talking all about the X-ray part, which is within 0.3 to 10 keV range. And then for all these sources, let's find for the multi-wavelength counterparts in optical, IR, and radio. So right now the radio counterpart is done, but the optical and IR still missing. And then based on all these 1, 2, 3, 4 steps, so let's classify the sources and then try to find out the distribution of different classes of X-ray sources in different nearby galaxies. And then once you had all the parameters, you can work on study on the correlation between radio and X-rays for these sources. This is the primary goal with which we have started working. Before going into our work, let me briefly introduce you to IIT Hyderabad campus. I think only Kuntal and Kumar was there, but I would like to invite all of you to at least have a visit whenever you will be free. So this is our old building, and IIT Hyderabad started with these 3 buildings in 2016. Now this 3 goes to around 19 buildings around. So all departments now have our separate buildings. These are the hostels at the bottom, and then this is our physics building. So this is 6 months back. This picture. Now we already shifted to the new physics building, and then we have courses or research going on all different types of topics, all the way from the transportation, AI, energies, climate change, nanotechnologies, sensors, devices. We have 16 departments, and then we have mostly they are engineering departments. So we have collaborations and inter departmental PhD programs. So a PhD student can work on 2 different departments, one with as a supervisor and co-supervisor. And this is my group. So I have 5 PhD students as of now, and today I'm going to present some work which did by Saurabh here, and Anurag and Megha is here. They are also visiting with me. Shri and Vishal and Saurabh, they are mostly working with the different X-ray topics. So she is working with the covariance spectral modeling and try to understand the X-ray variability of different variable AGN sources. Saurabh's work I will present, and Vishal works on the X-ray polarization studies of different bright variable X-ray sources and try to correlate the spectral state with the polarization measurements. And this is the one facility we just have installed. It's called ADO. We name it Advanced Dark Sky Observatory, and it was inaugurated by V. Radhakrishnan almost a year back. So right now we are setting up a half-meter telescope onto this facility. I mean, it's already installed, but the calibration is yet to done. So a part of my visit here is to understand and learn some techniques of the calibrations from the experts here. So this is the kind of activity we are doing here. And then moving on to my actual work. So basically the question that we ask, like, so how much do we know from the different populations of X-ray point sources in the nearby galaxy? So basically this is the first question that we ask, and then we try to understand using the best X-rays and the radio samples available. So X-ray surveys, there are lots of X-ray surveys have been done starting all the way back to I think 90s, and then still going on. And then X-ray surveys, they mostly provide you the different fluxes, point source, lots of X-ray point sources along with few parameters like X-ray flux or X-ray spectral stiffness. But the problem is, based on flux on stiffness, can we really do the classification works? Classification means here I am talking about the classification of X-ray point sources. For example, low mass X-ray binaries or high mass X-ray binary or supernova remnants or very distant quasar, which all comes under the category of X-ray point sources or pulsars. So far, we have, like, we take this kind of a Bible, this particular diagram, which was proposed in 2003 by Prestwich, which you can see on the left-hand side. So basically, the idea is if you calculate the colors, one is called X-ray hard color and the y-axis soft color. So hard color and soft color definition is shown here on the right-hand side. H, M, and S, these are the 3 bands. So basically the X-ray flux or the count rate in 0.3 to 1, 1 to 3, and 3 to 8 kV, soft, medium, hard. So we calculate these 2 numbers a CHM and then CMS, and then you plot them in this diagram. So in M31 Galaxy, Prestwich first proposed that if you calculate soft and hard color of these point sources, and then roughly these 4 circles tells you where your different types or classes of point sources falls in. For example, thermal supernova remnants are at the bottom part, or the high mass extra-binary are shown in the top right, and then low mass and the more absorbed source on towards the upper sides. So that he did, I mean, the group has done this work based on individual data, and then they fit with the spectra with some model. And so you can see the power law index for different types of sources. But this is a very small sample size, and then they have done 2003. But then using the bigger samples, using Chandra deep field samples with 383 galaxies and all the sources in the galaxy, Liu et al., Jingfeng Liu in 2011, he published this work on the right hand side, and then he used the exact same definition for different classes, the supernova, LMXP, absorbed sources, and HMXP. Now, if that is the case, and if we believe this is true, then if we just simply calculate these 2 numbers, we can say, okay, roughly where these sources are falling, or what is your source, without doing any further analysis. But then this scheme, which we believe for a long time, what we find has some problems, and which is basically how do we proceed with this particular project or work. So first, all these dots you see here are individual X-ray sources from different Chandra fields. I just quickly go through that how we can detect this X-ray point sources in this particular diagrams. There is a particular technique. I think this is also been used for other detection, other method detection of for other fields. So it's called wavelet detection. So basically, you have a scalable oscillatory function or wavelet, which you convolve with an image, and then one part of your convolution function works as a background, and then you compute a probability of finding this number SXY, basically getting the image, convolved image for a given threshold. So if SXY is less than the user defined threshold, then you identify that source pixel. And then you use the source pixel to get the VXY. VXY is basically the backgrounds, and then try to iterate to find some significance of a given source pixel. This is a tool which is also inbuilt in Chandra, and this tool works quite well for a long time. For example, if you compare the same tools called wave detect along with cell detect, which basically means you have a cell in your image, and then you compute the total counts in the cell, and then you slide the cells, and then you compare again the counts. This technique and then VTP technique, if you compare different techniques for detection sources in different fields, then wave detect actually performs really well. So here is a comparison. You can see the spurious percentage spurious detection in the wave detect. This particular table is taken from the Chow website, which basically gives you the lot of information on how different tools have been tested using different actual data sets. So for wave detect, they found like almost 0% spurious detection in the all different Chandra fields. So right. Mm-hmm. So for a given set of pixels, what is the significance or what is the probability that pixel contains a real source compared to the one which is the nearby pixels?
So how do you define a real source there?
No, it's like a threshold on the probability basically.
Yeah, that's why I was thinking if it is a single image you are applying.
Mm-hmm.
So the simple thresholding you did not try or not?
Simple thresholding, yes, that is also we tried,
Mm-hmm.
but then there is a issue with the spurious detection for this artifacts like which
Then
are.
what is the additional thing wavelet is adding? That is what I'm trying to think.
I think So it calculates, it's basically, it's maybe not adding something special, but it calculates more iteratively, which means you have different scales. So basically you define different pixel scales, and then for all different pixel scales, if your significance matches, means above your threshold significance, then only you define that as a real source. Mhm. No, only this one, because this is quite, I mean, for a long time it was used for Chandra.
Take a longer time than,
This takes longer time.
yeah, this wave detect takes a longer time.
Yes, yes, right, yeah. I mean, depends on like how much.
So the Penn State people has made some deduction things, and
Okay.
there are some Italian group they have made as well. So
Okay,
they are much faster than this.
okay, I'm not aware of that, so I can check. Algorithm. So yeah, this is the, once you run the wave detect, you can see this is one Chandrasic field in the X-rays, and the circles are the detections at in different chips, you can see, and then the size of the circle also give you the PSF size, and the significance is also been listed. So basically these are the kind of detection given by the wave detect. But now this is been used for long, but then there is a catch here. So you can see here we are trying to see sources which are actually distributed over the entire chip of the Chandra-ASIC in the X-ray. But then the question is, can we completely rely on this detection method? Means whether all these circles which are shown here are real sources or not. Now the problem is, in 2004, Kim et al., he showed that, he is a part of actually the Chandra team. He showed that there is an issue here. So the issue is, if the source is on axis, so these four plots are showing in the x-axis is the background counts per pixels, and the y-axis gives the detection probability, and these numbers here are the total counts you have for a given circle and or for a source. So if the source is on axis, for example, then if you have total source counts like 22, then you have detection probability of 1 irrespective of your background counts per pixels. So it's almost constant. But as you move away from the central focal plane or the central pixel, so for example 2 arc minute, 5 arc minute or 10 arc minute away, which means you are talking about the sources which are spread over the entire chip, then there is a fall in the detection significance because with the increasing the background count. So if you are 5 arc minute away, then if the total number goes from 90 to 18 or 7, then you see the significance falls off. And even if you are very far off, 10 arc minute away, then with increasing background count, even if you have 29, 36 counts, still you have far off, like your detection significance or probability is much lower. So if we do not consider this fact into account while talking about the sources in our sample, then there is a chance or huge chance that if your source is at the edge of your chip and it has a less counts, if your background is significantly high, then it might be a spurious detector. Okay, so that is the reason in our sample we actually
The off axis, then we have as well the PSF is quite degraded. It's ellipse.
it's an ellipse, right?
How do you take care of this? For example, if two sources are there.
So for example, here you can see, yeah, at the edges, you can see mostly they are the ellipses. So basically, I mean, these numbers, even those ellipse contains close to 100 or 100 plus counts, then it is probably that more chances it to be a real source than a spurious detection. I mean,
No, I'm not talking about that. I'm saying if there are the two sources, because
Huh.
the PSF is degraded.
Right, that we cannot actually say. So basically, you can see in most of the cases, sometimes they overlap if the PSF, and then in those cases, actually we omitted, and also the one which is falling on these cheap boundaries, those cases we also have omitted.
Do you see the manually also these things, or
Yes, yes. Each and every field we after running this we check
you check the
manually.
manually?
Distinguishing means we are relying on this wave detect output, which tells you the significance. So basically, significance, this 100 number is basically after subtraction the background. So it
takes-
estimated a background.
Yeah, it takes the background. You just specify the area of the source. It takes beyond that area. If it detects another source, if you count increase, then it doesn't take it.
So another way of saying
Local
that,
background.
let's say consider, and also so in this algorithm they can take out all these sources first and then make an average background counted, and then they subtract and calculate the significance. Quite low, but that also depends. In this case, you can see the first and third chip has much higher background. That brightness is due to the background compared to second and fourth. So it depends. Like if you are taking the earlier results around 2000, 2003, the chip was quite good. But now if you're taking the result from now, there are lots of issues. So
5 years.
yeah, 25 years, yes. Okay. Oh, okay. So basically, for all these 211 fields, we have here is a plot of detection significance and the number of sources. So you see most of the sources are having a significance less than 10 or so, and then number of sources with high significance is really small. I mean, that is what it expected. But here at around at the end, where the detection significance is really high, these are actually the AGN codes, which are strong X-ray emitters. So that's why the number of sources around 211. So this is 211, and then those appears the brightest one or the most significant one. And then this is also the source count, because that is our main criteria. So you can see as we go above 100, the number of sources also falling fast, and then again around here it has a good number of sources. But then if you put them together, so this is the actual total number of source. So basically these 211 fields contain, the wave detect returns around 6,800 sources close, and then we apply this additional filtering having 100 counts or significance higher than 20. So we end up with the sources which are in the +X +Y quadrant, and of course we are losing many sources which could be real source. But our aim of this project is to characterize each and individual source based on the timing and spectral results, which I'll show now. Okay, this is just a small numbers. So we have started with the 211 LeMMINGs sample, which actually also contains H2 galaxies and starburst galaxies and not so strong core X-ray emitter. So we end up around 167 sources, 67 field, which contains 8,574 detection. That number is coming from the wave detect, and then above 6 sigma around 4,000 detection. And then if we apply this number 100 counts, so we end up around 1,086 sources, including all. And then people have already worked on the ULXs in this field. So there are 186 ULXs already reported. So we exclude them. So we end up around 900 sources. And so all 900 sources we want to characterize one by one, just to see whether we can classify or we know what is the nature of the source using the characterizations plus multiwavelength counterpart. So this is an example, like this is the one which is shown by the wave detect for one of the field. And then if you apply the 100 counts, then we just end up with one source, which is shown here. I mean, that does not mean this is not a real source. This is again a real source, but we cannot characterize the source because the number of counts is much less. And what we mean by the characterization? So here, this is one of those faint sources which is excluded. You can see the X-ray spectra. This is the X-ray spectra from the Chandra, and it hardly have like 5 bins or 5 in your spectra, and then you can just barely fit a power law to this. And this particular spectra contains only 58 counts. So if you compare with another quasar spectra, which is at a redshift of 2.9, and it has 126 counts, so you can see the spectral quality improves. So that's why we keep this as the threshold level. Like, we'll consider all the sources having counts 100 or above, so that we can get a decent spectra. We can constrain the whatever power law or absorption in that particular source. So this is the X-ray image of that particular source, and on the top, that is the pan-star image, optical here. And this is another field where you can see the importance of this work. Now I'm trying to bring here that although these sources actually looks very similar, this is one of the IC10 field. IC10 is very famous for lots of ULX and other lots of activities in X-rays going on. So for example, let's say if you take one of the source called source number 3 in this image, and if you plot the light curve is basically the time series in X-rays, X-ray counted as a function of time, and you see there is no such variation, or I mean the count rate is really out of statistics. You cannot make much out of it. But then when we look at another source here, source number 1, and then you see initially the counts are really low, and then suddenly something happens to the source, and then X-ray counts goes really high for the quite long time. I mean, we have now the data which is above 100 kiloseconds, and we found that this is a X-ray outburst, and all these sources have not been studied before using such long X-ray light curves. I mean, that is one purpose of this particular project or survey, that that particular diagram which I showed at the beginning, it tells about LMXPs, HMXPs based on the position, but do they really fit as per our more detailed analysis?
The background and all.
No,
Background
because
photon flaring and all.
no, these light curves are all background subtracted. So background is studied separately and then subtracted, and then this is what we saw.
Okay.
And also not just, I mean, this is just one thing. For the another next part, we take out the spectra of this one, and then we model the spectra and then compare how which classes of the sources does the model, I mean, similarly. And this is the spectra. Okay, coming back to your answer. This is the spectra of that particular source. And here you can see that if you just use a power law, which previously those guys, I mean, Liu and Prestwich used, they arbitrarily fit single power law to each spectra and then try to conclude the different types of sources out of it. But that does not happen here. If you just simply put a power law, it does not really fit. You need to have something else, I mean, addition to the power law. So that is the motivations for this work, that, okay, it is a bit painstaking because all 1,000 sources you have to check individually one by one, but it makes sense. But there is another interesting aspect of this. For example, this is one of the field which is observed in pan-star. So the right hand side is the pan-star image. These are two optical, two stars you can see here. But then if I superimpose the pan-star image on the Chandra image with the same coordinate matching at the same time, at the same time, then this particular source actually appears in the Chandra image. So the red one is Chandra. These white stars are the same star which you see in the pan-star image. So at least Chandra shows sometimes the X-ray source gives us additional information, like this source present there in between the star you cannot see here in the optical image. So that brings the importance that along with, I mean, Chandra itself is very important because you see lots of X-ray activities going on different galaxies. But now we have to also combine with the multi-wavelength, means the optical. Why? This gives you some idea. So this one, yeah, this one on the right hand side, this is from the galaxy field NGC 1961, and this is actually a very famous ULX in NGC 1961. It was thought to be an ULX for a very long time. I mean, there are lots of publications considering this is a ULX which is associated with in 1961. But later, using the optical data, this is the optical counterpart of the same one. They found that this has a redshift of 0.8414, and it has not. So the galaxy does not have that much redshift. So this source is not associated with the galaxy. So this is not an ULX. So finally, they found that this is a AGN, which is at a large distance. Similarly, the one on the left is first decided as an X-ray binary using the X-ray, but later it found that this is a kind of X-ray flare which is happening in one of the white dwarf sources. So in this way, if we do not connect the multi-wavelength properties of these point sources, then probably our understanding of the classification would be very much incomplete. So now what we do, this is our sources, like 1086 sources, and then we have calculated the same one, the one which is suspicious or doubtful, the classifications based on hard and soft color, and then we put the same circle here, okay, exactly same circle that they have done, and then we are trying to understand that whether this classification holds when we know all the properties of the sources. Okay, so this is, sorry, these boundaries. Circle boundary is coming from that Prestige paper, 2003 work, where they have defined this boundary because all the SNRs, thermal SNRs are contained within this boundary. So we assume that whatever SNRs present in our sample, they must be within this boundary. This is our assumption. This need not to be true, actually. So which I will show, I mean, that is the reason. So anyway, this work, X-ray work is almost completed, and it is all done with the spectra and the other property study. This is the Paolo distributions for all the sources they have found in 2011 data, incorporating each and every points here, 8,000 data points. But then when we studied with our sources, we actually saw that actually there is a difference in the distribution, although our numbers are much lesser compared to the other one. But there is a distribution pattern which is, I mean, this is not with all the sources, few hundred sources. So there is a peak in the number of sources if you plot the photon index distribution, which is closer around 1.7 PI index. And then there is another peak which is going up here close to above 2 or above 2. So, and then there is one more distribution which is around 1.6, which actually much flatter. So it's not just one single distribution we saw. There are multiple peaks of this particular distribution, which will update. So just I will finish with two more examples of this particular work. That first we started with all the so-called HMXPs, like let me assume that all this green circle, or at least the rightmost part of the green circle contains the HMXPs. And I pick up one of them, for example, the one shown by the arrow. And Chandra has really long observation for all these sources. So we combine all 13 years of Chandra data here for all different observations IDs, and then we try to find out the optical counterpart or infrared counterpart, but we found none actually in that particular locations. So some of the field actually covered by the HDSS survey, and I think they have, if there is no report, I mean no detection in their field, so some of the papers actually reported the level of detection is around 19 or 20 with these surveys. So there is no detection, but then once you plot these light curves for all different sources, you can see here that we start here. So this is in month, 180 means almost 15 years. So most of the observation is done here, and you can see, so once you remove all these gaps here, sorry, all these gaps here, and if you plot them next to each other, it's more or less very constant. I mean, there is no changes in the light curves or the count rate. And then you carry on the spectral analysis of all individual sources. So this is a table which shows the spectral parameters. I just want to point out, not to read the whole table, but to point out few points, that basically what we see in most of the high mass X-ray binaries, that they are quite absorbed. So absorption column density is really high, which we see throughout 15 years of data, starting from observation 1 to observation 12, the first column. And then they have a photon index which changes abruptly, from 1.85 can go all the way to 2.53, which we also see. And then they do not change. I mean, the light curve do not change with time. So more or less they are consistent. So this source, based on this study, so you can see the PI index changes, I mean, going up and down and always close to 2 or 2.5. And secondly, the NH column density also changes quite a lot over a time scale of 15 years. And so these two facts, along with the stable X-ray light curves, tells us that most probably this is one of the high mass X-ray binary, because that fits into the criteria. So our green circle contains the HMXP, and this one is from the green circle, so there is no issue with this. But then I choose one more source here, which is shown in this one. And then again, we have all the 13 years of data for that source. And here we do see, again, the same thing, the light curve on the top. Okay, these are the gaps in the light curve, and these are the end. And then if you remove the gaps, they look more or less like this. So there are some flares which is going up and down, and there are strong variability even within the observations you can see in different things. And then if you do the spectral modeling using Chandra X-ray, and then you see here there are interesting things. First, the column density is much lower. I mean, it is lower not just in one observation, it is lower more or less in all observations, which is less than 1. But the one which are dotted here is basically the one where we use the galactic absorptions. We fix it to the galactic absorption. No additional absorption is required. And you can see here the power law index is much lower. None of them actually goes at 2. They are all almost below 2. And the flux is quite variable. So this is the PI index variability here. You can see it goes up and down, but it's always close to around 1.6 or 1.7 throughout 15 years. And then the NH is also much lower. So these two are properties which are very different from most of the HMXPs, but they are very similar to most of the LMXPs that we see. Based on this, we interpret this is a low mass X-ray binary.
If you fix the NS to the galactic column density, whether it's needed, I mean, you fix it the galactic column density, and we just look into the fit, whether the fit
right.
or not.
So basically, what will happen if we keep it free? Then it actually reaches to the, I mean, by itself it reaches.
That's what I'm saying. You just keep it a fixing for all the observations and then check to the.
Yes, then it does not work, and that's why we have to keep free the other one. So this one does not work at the galactic column density, so we have to keep it free and free to vary.
So this accounts for the only galactic column density, right? Not the your own one.
No, this one is the only galactic density.
Exactly.
This one is the addition to the galactic density.
Even if we just look into that, this is only the upper limit is looking at yes. For example, observation 3, the lower limit and the value is quite.
Yeah, yeah, right. Yeah, you're right. Yes. I mean, that is, you can see here also in this plot. Yeah. So yeah, it touches 0 here, okay,
Yeah.
in most of the cases. So anyway, the idea is the NH is really, really low. I mean, it does not need to be that in HMXB, it's at least 10 times 1 order of magnitude higher than what we see in average in these cases.
So what is sorry, I'm sorry. What is the value of galactic NH towards that direction?
In this case, IC10 it is 1.6 10 to the power 19.
Oh, it's quite low.
Yeah, quite low. 10 to the power 19 per semester. So anyway, this source is now well within that green circle, but now these properties are more similar to low mass extravagant, not high mass extravagant. So that makes us think that, well, this scheme might need to be revised. And then I just want one more cases for supernova remnants. So we found this 6 sources which are within the SNR circle, and then we try to see in few cases. For example, this is one of the sources which are in this circle, and here you can see this is again the same 15 years data, and then if you remove the gaps, the light curve looks like this. This is an interesting case because the supernova happens during this time, and then we expect this to fall, I mean, which is fine, but then with time you can see the X-ray count rate increase a lot, I mean significantly increase over tens of years starting from here, and then suddenly it falls here. So we are not sure yet why this happens, but what Ian proposed that this might be the supernova might create a neutron star at its center, which may accrete material from nearby environment, and that accreting material can give rise to the increase in the X-rays. So basically, we might see a formation of accretion disk in this particular case for like a neutron star X-ray binary, but that is not sure. But we do see an increased X-ray emission, and then it goes down here. Right, but whether it will form a binary, I mean, accrete material, that I'm not sure. I mean, formation of neutron star is fine, but I mean, do we expect to see an accretion disk in all the supernova? I'm not sure about that, because we don't see that scheme in other supernova. This one is kind of a bit special in that way. I'll show you one more examples. Okay. Yeah, that we don't know. That is the one thing. This is too much mysterious, to be honest. We don't know, really, we don't know. I mean,
Maybe
but the thing is,
material which is ejected is now stagnant there. I don't know.
yeah, yeah. So basically, that's why we started working on the individual spectra. But the thing is that these are the spectra for 3 different fluxes, the 3 extreme fluxes that we see here. And this is the typical spectra that we see from in X-ray from supernova. And it does fit with the typical models which people use for the supernova modeling. So this is definitely a supernova, and then we see the signature in X-rays. And at the parameters we find from the X-ray spectral modeling also fit with the supernova model, but it was not reported anywhere. I mean, we don't find anything like it was reported as an X-ray source, almost close to the or matching with that particular position of the source, but no supernova reporting was there. So yeah, it is supernova, but we are not sure what happened in the later time of that particular cases. And then this is the one, basically it's the X-ray position, and this is the optical position in the galaxy of that source. Then we have taken another source from that particular circle, supernova circle, and then here you can see that the that's the same scheme. First, the supernova started here somewhere, and then it all goes to almost quiescence, nothing happened. Some activity around here, and nothing here. And then at the end, somewhere here, there is sudden flaring kind of activity going on, which is, this is the recent one, but this is 15 years back, almost 12 or 11 years back. Now, the problem here, what we face, that even if you take the spectra of all this data, none of these spectra actually show the signature of a supernova. So basically, the spectra can be fitted with a model which is pretty much similar to what we observe from a X-ray binary, a low mass X-ray binary typically. So again, we are in a trouble that the classification of SNR, and then once we pick up one by one and try to see whether that's a real SNR or it is a X-ray binary, as per the X-ray analysis, it does not fit. So we really need some kind of multi-wavelength help in this regard, which could actually sort out these issues. Okay, so anyway, we are almost done with the HMXPs and SNRs and ULXS part. The LMXPs, we have started working on it. And then in between, there are lots of X-ray transients which we have observed. We keep them separate. I mean, we don't know where they're coming from. And then lots of, not lots of, and few tens of quasars, background quasars have been observed, which was not reported earlier in X-rays. Okay, so we are trying to now develop this whole survey catalog for individual sources, the X-ray, the long-term X-ray spectral variability, timing variability, and then the multi-wavelength counterpart of each of these sources. And for optical, probably the facilities here. So far, we are actually working with Gaia and Pan-STAR survey data and taking their fluxes if available. But there are many which we don't see or don't know. I mean, if they're there, so probably we can try something, if possible, from ARIS facility here for the optical part. For infrared part, I am collaborating with Mount Abu facility, Professor Vishal Joshi. And radio, we are using e-MERLIN and VLA images to find out the radio counterpart for these objects. Okay, I think that is my talk. Thank you very much.
Will I ask?
Yes.
You're not looking for any stellar sources
In our galaxy, no. These are all,
because we have enough sources that may have X-ray counterpart.
but I guess most of them are done. I mean, people
Not
already know.
necessarily, but they may be the faint sources where you may be misclassifying them with the galaxies and all.
Yeah, I mean, that would be a nice addition. But yeah, I mean, in our galaxy, this is not included in this particular survey. But that would
Because
be
the Chandra, even if Chandra images, they have enormous stellar sources are there.
exactly.
Yeah.
I mean, yeah, once we'll finish, we might come back to this one. That would be a nice addition.
So in the image where you showed superimposition of pan stars over the Chandra thing, right? So there, why are the sources offset? What is the reason? Are those same source or it is the same source, right?
Same, the stars are same. Yes.
Same. But why are they offset compared to pan star?
I think I zoomed one cases, it's zoomed out and zoomed in. Offset in the sense the difference.
Are those three different sources? The two stars you see in pan star, and then the central source you see in
Central source is only in X-ray, not in the pan star.
Yes, but are those three related to each other or different?
That we don't know yet.
Yeah, that is another my question actually related to that. So how do you counter for the multiple identification?
So far, what we are trying that within the Chandra has the spatial resolution of 500 milliarc seconds. So if we see anything reported within the 500 milliarc seconds, then we consider that as the counterpart.
Exactly.
But then most of the cases we do not find much information about that.
But at the same time, we are looking with the Pan-STAR, right?
Pan-star, right?
So pan-star has its own, so it's again a
Yes,
second
yes. So
like that.
yeah, most of the counterpart that we found from Pan-star only, but many of them are missing, so that we don't know yet.
So why don't you use then other than pan-star and other garbage and all?
Other
Which is a
means
better,
HDSS service.
yeah, which is a better.
Yes, yes, yes. I mean, those which are missing are not still not present in HDSS. So probably either that field might not be covered by HDSS or the magnitude did not, I mean, HDSS did not look for sufficiently long time to detect those sources. I mean, usually what we expect LMXPs and HMXPs counterpart have magnitudes around 21 to 24.
They're
So
going to the stomachs data and all.
2 mass, yeah, some of them are there, but not all of them. That's the thing. So there is a lot of missing part still.
Mm.
I have one question. Like these supernova, you are telling that these are binary systems, something like that?
The one last but one, you're saying?
Yes.
Yeah, that is what we guess, that it actually forms a transient accretion disk around it from which the X-rays are coming. So it's like a building of the accretion disk around it.
Okay, but the X-ray flux can be also coming from the supernova only, no? Maybe the supernova shell and the magnetic field, something like that. Is it-
But like so the time scale is around, I don't know, time scale is around 15 years.
Yes.
But we expect something goes after 15 years of supernova, like sudden increase in the X-ray.
There
from the
should be a pattern,
supernova.
like the magnetic field either decays, so there should be a pattern.
These are remnants, right?
Okay.
Hmm.
You are seeing the flux from the remnant.
Remnant, but which is increasing rapidly.
Mm.
Which I,
Is it due to the accretion if we are talking about that?
yeah, that is,
central star is something now it's secreting and material and all.
yes,
Yeah,
yes.
the
that
neutron
is
star, you
neutron
said that
star
the neutron star, which is accreting at that point of
at the,
time.
yes.
But that you don't see in the other one.
No, I don't see. No.
Interesting.
But if it is like starting from 0, let's say 0 to up to 15 years,
Hmm.
so the initial part is from the supernova flux, or
Yes. That is identified as a supernova at that time.
and then over time it changes to the remnant and gives you the flux from the
Plus
remnant.
from the remnant and some other stuff. Which
The remnant looks like a point source also.
No.
it's no
No, it's
in
very far. That's what I'm saying. It's a point source. Then you can do that. With the remnants have larger this one. Then the size is again the while doing the reduction, the taking of the source edge maybe the
No,
No, I think in Chandra will it appear as a point source
point
only?
source, yes.
Because there are certain remnants like over time, because you will see the expanding shell also. So you will see the morphology. Maybe that is very late in time, like about 30-40 years
Okay.
after the supernova explosion. Because that's what has been seen in 1987A. One
Okay.
is able to clearly see the rings,
cells.
the shells.
in X-ray.
Yeah.
In X-ray,
X-ray, optical, IR.
the X-ray that much of the heart of the cell.
I wanted to ask on the classification you mentioned, based on that indices, essentially they're telling how much of soft X reflex and how much of hard X reflex, right? That is
Right,
present
right,
in
right.
components of that.
Yeah.
So in that sense, I mean, is there any physics associated with that categories saying that if you have for LMXBs or for HMXBs, so you should have higher amount of soft X reflex, or based
That
on
is
that, or
what, yeah, that is what it presented here, that paper.
but
That
then you
is a-
can you draw a circle there exactly like saying
that is not correct. I mean, should
Okay.
not draw a circle. I mean,
so
that is one
when they have drawn initially, so
Yes,
the
yes.
logic was they already know these sources are from LMXBs and then draw a circle, or they draw from the
No.
amount of X reflex.
Yeah,
or-
50% of that they have done properly, but remaining 50%, since they are falling on next to each other, so they put it into one group.
Okay.
So that's how it works. But anyway, people are blindly following that. So we are now suggesting, no, don't do that.
Nice. Thanks.
Point I just wanted to mention is that for these supernova remnants, so did you try looking at the Fermi gamma ray light curves of these supernova remnants? Because after Fermi, there have been a lot of SNRs which have been detected in the hard bands.
Yeah, this SNR also been detected in Fermi, but I have not checked the light curve yet.
Yeah, we can, maybe you can check that the variations that you are seeing here, the rise and the drop of the flux, whether it's the same behavior in the
Fermi.
Fermi also.
But when Fermi was launched, I forgot. Wait, okay, so this start from 2000 onwards. So first 8 years might be missed. So anyway, the last part we can have. Yes, seeing that one. Yes.
Yeah, I have another point, like in these surveys like nearby galaxies, do you also cover starburst galaxies?
Yes, they are also.
Okay. So do you have any point source
Yeah,
population?
yeah. This 1080 sources in our list. It also contains the sources from starburst galaxies,
Okay.
like NGC 1275 also.
Okay, thanks. So if no more questions, let's thanks again the speaker for the interesting talk.
Thank you. আচ্ছা তুমি থাক আমি আছি শনিবার পর্যন্ত সময় পেলে গেস্ট হাউসেই আছি